Welcome to Module 53 in this series of lectures on statistical quality assurance and statistical process improvement. We're now ready to talk about not just half fractions of 2 to the p factorial studies, but smaller than half fractions, quarter fractions, eighth fractions, 16th fractions, and so on. That is, the subject here for this module is the choice and aliasing patterns that go with the choice of smaller than half fraction studies, half fractions of 2 to the p studies. The issues to address in the analysis, the choice and analysis of fractional factorials are the same as those that we've just looked at for half fractions. In general, the issues are how to choose a quarter fraction, a half fraction, an eighth fraction, a 1 over q fraction of the 2 to the p possible combinations to use in a study, how to determine the corresponding pattern of alias or confounding, what's inseparable from what, and how to do data analysis. The answers that one can give for smaller than half fractions are really just the natural extensions or generalizations of the ones that we've already discussed in the previous couple of modules for the half fractions. To choose a quarter fraction or an eighth fraction, a 1 over q fraction of a 2 to the p factorial, here's what we're going to do. We're going to write out signs that specify all possible combinations of the first p minus q factors. So where there was going to be a half fraction, q was 1, and so we wrote out signs specifying levels for all possible combinations of the first p minus 1. If it's going to be a quarter fraction, it's going to be p minus 2. If it's going to be an eighth fraction, it's p minus 3, and so on. And then we pick out q different groups of the first p minus q factors and use the products of signs corresponding to the members of the groups to specify levels for the factors that whose levels are yet to be chosen. Here's an example, a real example, taken from a paper that was presented at a national meeting of the American Statistical Association on an experiment for the development of a catalyst. It involved 5 factors. Factors A, B, C, D, and E, a couple of temperatures, chemical ratio, precipitant that was used, and support used for making the catalyst, each at 2 levels. So there was a low level and high level of each, and there was a well-defined response that was the percent of water produced using those various combinations. Now, there are 5 factors. If one takes all possible combinations of those 5 factors, the requirement would have been to make 32 different catalysts. In fact, the investigators decided against that and rather decided that they wanted to consider only a quarter fraction of the 2 to the 5th possibilities. That is, they ran 8 out of the 32 possible A, B, C, D, E combinations. The choice that was made for designing that one quarter, that is 8 out of 32 of the combinations, was to use an ABC sign product to choose levels of factor D and a BC sign product to choose levels of factor E. That is, if there is going to be a 2 to the 5 minus 2 fractional factorial run, one first writes down signs for 5 minus 2 is 3 factors, that is A, B, C, and then makes choices of some groups of those letters A, B, and C to make products for choosing levels of the remaining factors D and E. This is the choice that was made in this particular real study. There are other possible choices, but these are the ones that were preferred by the engineer in charge here, and this is what we're going to work with. This is summarized here. So there are A, B, and C, 3 factors, for which in this part of the table I've written out all possible combinations of plus and minus signs, low and high levels for A, B, and C. By making ABC products, one gets this set of signs, and those are used to set levels of factor D. By making BC products, one gets this set of signs, and those are used to set levels for factor E. If one reads across then this first row, one sees that A is at its low level, B at its low level, C at its low level, D at its low level. Only factor E appears at its high level. That is combination E in a 5-factor study. Similarly, on the second row, if one reads across, one sees A high, D high, E high. That is combination ADE in a 5-factor study. There are 8 out of 32 possible combinations of levels of factors A, B, C, D, and E. That is a 1/4 fraction of all 32 combinations. That is a particular 2 to the 5 minus 3 fractional factorial. It is the one that was used in the study. Here, just to make this as concrete as possible, here are the data that were reported by the investigators. Combination E, there were 3 runs made with that kind of catalyst for a Y bar of 9.767 and a sample variance of 2.543. There are the raw data values, and so on. Only 3 of these combinations had more than one observation. So this is a partially replicated fractional factorial. It is these 3 sample variances that get pooled together to make a pooled S. There's nothing wrong with that. There's nothing that requires this to have equal numbers of observations per combination. There's no requirement here for data balance. To understand the pattern of ambiguities that one faces when one does a smaller than half fraction, what one must do is to write out a generator for each of the factors beyond the first p minus q of them. Multiply those generators, turn each of those generators into something of the form I is equivalent to a string of letters, and then multiply them together, list them, and then multiply in pairs, in triples, sets of 4, and so on, to end up with a string that says I is ultimately equivalent to a series of products, exactly 2 to the q minus 1 of them. So here's an example of that for the Hansen and Best catalyst study. The two generators for the experiment design were D, levels of D were gotten by ABC products, levels of E were gotten from BC products. If I take this and multiply through by D, I get that. If I take the second generator, multiply through by E, I get I equivalent to BCE. If I then take this and multiply by that, both sides, I get I by I, equivalent to the product of A, B, C, D, and BCE. On the left side, I by I is I. On the right side, there's only a single A, a single D, and a single E, with B and C being represented twice. And so I get another of these equivalences for letter I. And so when I string those all together, I get I equivalent to A, B, C, D from up here, BCE from up there, and then ADE from this product. What that means is that effects are aliased in 8 groups of 4. The grand mean here is indistinguishable from an ABCD 4-factor interaction, a BCE 3-factor interaction, or an ADE 3-factor interaction. This is the defining relation. If I multiply through that defining relation by A, I see that the A main effect is aliased with a 3-factor interaction, a 4-factor interaction, and a 2-factor interaction. So that's the same kind of method that was used in the case of half fractions. It now just gets extended to more letters and more products in that defining relation.